Hello, everyone. It's wonderful to have you all here today. We are about to embark on a journey into one of the most extreme environments in the known universe. Our lesson is titled Introduction to the Abyss, and over the next several segments, we will uncover the mysteries of black holes together. Let's start with the core concept. A black hole isn't just a hole in the traditional sense. It's a region of space-time where gravity is so incredibly strong that nothing, not even light, the fastest thing in existence, can escape its pull. Think of it as a place where the fabric of the universe is curved to an infinite degree. If you look at this visualization, you can see how light from surrounding stars is warped and twisted around the dark center. This shadow is our first real hint at the presence of such a massive, invisible force. This brings us to a critical boundary known as the point of no return, or the event horizon. It's a theoretical surface where the escape velocity required to leave exceeds the speed of light. Once an object crosses this threshold, it is effectively removed from the observable universe. To guide our exploration, here is our roadmap. We will begin our trek at the outer rim's accretion disk, move toward the event horizon we just discussed, and eventually attempt to understand the hidden singularity at the very core. Are you ready? Let's dive deeper. Now that we've glimpsed the mystery from a distance, let's peel back the layers. Here we have the anatomy of a black hole based on structural models used by NASA to map these cosmic giants. First, let's look at the accretion disk. Think of this as a massive swirling whirlpool of superheated gas and dust. As this material is pulled inward, it orbits at such high speeds that friction turns it into a glowing ring of radiation that we can actually observe. Further in, we reach the event horizon. This isn't a solid surface, but a mathematical boundary. Beyond this point, the gravitational pull is so extreme that the escape velocity exceeds the speed of light. Once something crosses this line, there is truly no coming back. I've detailed the specific layers and their physical characteristics in this table. It's a helpful guide to how the environment changes from the high-energy chaos of the outer disk to the absolute silence of the horizon. You'll also notice a note about the Schwarzschild radius, or Rs. This is the specific distance from the center that defines where that event horizon sits. It's a fundamental calculation in astrophysics for determining a black hole's size. Keep these components in mind because next we're going to see how they actually warp the fabric of spacetime. Welcome. In this simulation, we'll explore Einstein's general relativity by visualizing how mass curves the fabric of spacetime. Use this slider to increase the mass. Notice how a larger mass creates a deeper well in the grid of spacetime. A standard star like our Sun has a large radius and relatively low mass, creating a gentle curvature that governs planetary orbits. Now, pay attention to the radius. As we shrink the object size without losing mass, the density increases, making the gravity well much steeper. With a neutron star, the mass is higher and the radius is small. The slope of spacetime becomes incredibly steep near the surface. Finally, look at the black hole. The mass is concentrated into such a small volume that the curvature becomes infinite at the center, creating a singularity. Try adjusting both sliders yourself. Observe how the extreme warping of a black hole prevents even light from escaping its event horizon. Now that we've examined the structural anatomy of a black hole, we come to the most profound moment of the journey, crossing the event horizon. As we saw in the previous pages, this represents the ultimate boundary of our observable universe. One of the most mind-bending aspects of this crossing is the perspective shift. What you see depends entirely on whether you are the one falling in or the one watching from a safe distance. If I were watching you from outside, I would see your clock slow down until you seem to freeze forever at the edge. But for you, the traveler, the experience is quite different. You wouldn't feel a thump or see a physical line. You simply glide into the abyss, though the universe behind you begins to look very strange. Once you are inside, we enter what researchers like Brenna Mockler call the inward timeline. This is where the standard rules of navigation completely break down. Inside the horizon, space-time is so distorted that space effectively rotates into your future. Just as you cannot move backward in time to yesterday, you can no longer move outward toward the surface. Every direction you look, every path you take, leads directly to the center. It truly is the point of no return. You are now committed to a one-way trip toward the singularity. Next, we'll explore the physical toll this journey takes on an object, the famous and slightly terrifying process of spaghettification. Now that we've crossed the event horizon, we need to discuss the physical toll this journey takes on any object. This brings us to a process with a very descriptive name: spaghettification. It sounds like something out of a cartoon, but the physics behind it are incredibly violent and fascinating. The first stage involves extreme tidal forces. As you fall in, you're not just being pulled, you're being stretched. Imagine your body as a piece of dough being pulled from both ends while being squeezed from the sides. This simultaneous vertical stretching and horizontal compression is what turns an object into a long, thin strand. This formula here represents the gravity gradient. In our daily lives on Earth, the difference in gravity between our head and our feet is negligible. However, near a black hole, that difference represented here by delta G becomes so immense that it overcomes the internal forces holding an object together. Essentially, because gravity weakens with the square of the distance, the pull on your feet is significantly stronger than the pull on your head. This gradient is what causes the stretching effect we just discussed. Finally, we reach the point of atomic disruption. This is where the tidal forces become so powerful that they even exceed the electromagnetic forces holding your atoms together. At this stage, any object is reduced to a stream of individual subatomic particles, accelerating toward the center. It's a stark reminder of how extreme the environment becomes once you've passed the point of no return. But where do these particles eventually end up? Let's proceed to the very heart of the black hole, the singularity. Following the intense stretching of spaghettification we just covered, we finally reach the destination of all matter, the singularity. This is the very heart of the black hole, where the laws of nature as we know them undergo a profound transformation. Look at these mathematical properties. We are describing a point where density, rho, tends toward infinity. It involves an enormous amount of mass being crushed into a volume that effectively shrinks to zero. It's almost impossible to visualize an entire star's worth of matter occupying no physical space at all. This is where we hit a massive physics limit. Because the curvature of space-time becomes infinite here, general relativity, our best theory of gravity, simply breaks down. The math starts giving us infinity as an answer, which is a sign that we need a more advanced theory, like quantum gravity, to truly understand this core. Now, why can't we see this breakdown from the outside? This is thanks to cosmic censorship. Nature seems to insist that singularities remain hidden behind the event horizon. This protection ensures that the naked singularity and its unpredictable physics can't affect the rest of the universe. Ultimately, the singularity represents the absolute boundary of our current scientific knowledge. It's the ultimate mystery box. Next, we'll dive deeper into why this abyss stays so well hidden from our telescopes. Welcome. Today, we will journey into the heart of a black hole to explore its unique layers and extreme physics. We begin at the accretion disk, a swirling mass of superheated matter spiraling toward the center at incredible speeds. You can use this slider to control the rotation speed of the energized matter in the disk. Click here to move closer to the event horizon, the boundary where the gravitational pull becomes inescapable. Notice the photon sphere. Here, gravity is so strong that light itself is forced into a circular orbit around the black hole. At the very center lies the singularity, a point of infinite density where our understanding of space-time reaches its limit. Having just explored the singularity, that point where our math essentially breaks, we arrive at the most frustrating and fascinating part of astrophysics, why the black hole remains the ultimate mystery. The core of the issue is a fundamental clash between our two greatest theories. General relativity explains the gravity of massive objects perfectly, while quantum mechanics explains the behavior of subatomic particles. But inside a black hole, you have something both incredibly massive and incredibly small. When we try to combine these two sets of rules, the equations simply stop making sense. It's worth noting that even Albert Einstein struggled with this. As recorded in the BBC archives, he was deeply skeptical that nature would actually allow a black hole to form. He questioned if a singularity was a physical reality or just a mathematical error in his theory. Then we have the information paradox. In the quantum world, information about a particle's state can never be truly destroyed. However, if that particle falls into a black hole, it seems to vanish from our observable universe. If the information is truly gone, it would mean our understanding of physics is missing a massive piece of the puzzle. To solve this, Stephen Hawking proposed that black holes actually leak energy called Hawking radiation and eventually evaporate. But this led to the firewall hypothesis, the idea that the event horizon is actually a wall of high-energy particles that would incinerate you instantly. We still don't know which theory is right. We've reached the final stage of our journey today. To wrap up our exploration of the abyss, let's reflect on the major concepts we've covered and why they matter so much to the world of science. First, we must view black holes as the universe's most extreme physics laboratories. As we saw when discussing spacetime curvature earlier, these regions allow us to test the very limits of general relativity in ways that are impossible anywhere else in the cosmos. We also looked at the Great Veil, the event horizon. It serves as a boundary that protects the secrets of the singularity. While it prevents us from seeing the inner core directly, it remains the most fascinating threshold in all of physics. The quest for knowledge is far from over. Modern research continues to peel back these layers. Every new data point helps us better understand the spaghettification process and the strange behavior of time near a massive gravity well. Ultimately, mastering the physics of black holes is a fundamental key to understanding the past, present, and future of our entire universe. Thank you all for your incredible focus and insightful questions throughout this session. I hope you leave today with a newfound wonder for the unknown.